In this section, we're going to look into another important component, which is ledger. So ledger stores important information about business objects, or also known as assets. So ledger consists of two parts. One is world state and the other one is blockchain, which is nothing but a transactional log. So the world state has two database options. One is level DB, which is default in Hyperledger Fabric. Then you have another option, which is CouchDB, where you can run rich data queries. So the ledger is a sequenced, tamper-resistant records of all the state transitions in the fabric, while state transition are a result of chaincode invocations or chaincode transaction invocation submitted by participating parties. Each transaction results in a set of assets, which are key value pairs that are committed to the ledger as the create, update, and delete transaction goes on. So the ledger is comprised of blockchain to store immutable sequenced record in blocks, as well as a state database to maintain the current fabric state. So there is one ledger per channel. Each peer maintains a copy of the ledger for each channel of which they are a member of. So query and update ledger using key-based lookups and range queries and composite keys are possible. So read-only query is using query-rich language. So if you are this can be used if you are using your CouchDB as your state database. So CouchDB is really good if you include it in your project, where you can actually run rich queries on the CouchDB. So you can also get the history of a particular asset by running read-only history queries. So query ledger history key for the history for a key enables data provenance scenario. So using a key of an asset, you can get the details of an asset, what all the states or what all the stages that asset has been through. So you can get the history of that particular asset. Next, you have transaction consist of versions of key or value or key value pairs that were in a read that were read in a chain code. So that is called read set, and the key value pairs that were written in the chain code is called write set. So the transaction contains signature of every endorsing peer and are submitted to ordering service. The transactions are ordered into blocks and are delivered from an ordering service to peers on a channel. Then, after that process, peer validates the transaction against endorsement policies and enforces the policies. So prior to appending a block, a versioning check is performed to ensure that states of an asset that were read have not changed since the chain code execution time. So there is an immutability once a transaction is validated and committed to the blockchain. So a ledger contains a configuration block defining policies, access control list, and other pertinent information. So the channels contain membership service provider or MSP instances, allowing for crypto materials to be derived from different certification authorities. In this picture, as you can see, you have a peer which is peer 1, and it has different smart contracts deployed on it, and it has different ledger. As you can see, you have smart contract 1 and smart contract 1 again, and you have smart contract 2. So you may ask why the same smart contract S1 is deployed on the same peer and it has different ledger. As we have seen before, for every channel, peer keeps a different ledger. So that is the reason you have two ledger, which is L1 and L2. This means this peer P1 is part of two channels, which is maintaining different ledger. One channel for the ledger, one ledger L1 for channel 1 and another ledger L2 for channel 2, and both the channel has the same contracts, same smart contracts installed on it. So you have this smart contract ES2 which has not generated any ledger so far. So this is not yet invoked by any client or any application. So that is it for the ledger section. In the next section, we are going to look into another component which is channel. See you in the next section.